Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
So this is a topic in combinatorics or question in combinatorics whose answer is provided primarily by probability, but also using some somewhat new traces. There will be two answers to the question, and one of them uses traces, one of them uses random walks. So you'll see what that is. Now, first of all, you can find a preprint on the archive and also on my homepage, and the paper will appear in CPC. Now, the topic is spanning trees and graphs, and actually this is thousands of years old. Oh, this didn't work. All right. So here's a little graph, 3 by 3 portion of the square lattice, and one of its spanning trees is thousands of years old, which is rather famous, and there's an alternate version of it which is infamous. But that's one example. Another example from 1300 on a mausoleum is this in Iran, although this is actually not quite a spanning tree. Now, I don't know if I need to define what a spanning tree in a graph is for anyone in the audience here. Everyone's fine with it? Okay. So actually, you can see this is not quite a spanning tree, although it looks like it. What it is square Kufic calligraphy for a widely quoted verse of the Quran. And it is sort of calligraphy called square Kufic, and it's a widely quoted verse of the Quran. It's on a mausoleum in Iran, built around 1300. This is from Stephen Wolfram's book, the illustration. I got it from there. Now, just for the final example, here in red is a spanning tree on a torus graph, square grid on the torus, and so this vertex out here is the same as this vertex over here, and likewise this vertex is the same as that vertex. So we're going to be looking at general finite graphs, and tau of G will denote the number of spanning trees of G. So I'll assume G is connected. There'll be at least one. The topic seems to go back to 1847 with the paper of Kirchhoff, who showed a connection to electrical networks, which also maybe everyone here knows. But just as for anyone who doesn't, one example is if A and Z are any two vertices of G, then the effective resistance between A and Z in this network, if each edge has unit resistance, is given by the number of spanning trees of G divided by the number of spanning trees where A and Z are contracted to a single vertex. And there are other theorems of similar nature. So what I'm going to do is just give some history first of some examples of what people know and why people are interested in counting the number of spanning trees in graphs. Oh, sorry. I guess I didn't need overheads with this kind of projection system. So I won't review it. This is a picture due to Rick Kenyon. But temporally in the 60s found a bijection between certain planar graphs, in particular the square lattice, of spanning trees on the one hand and tilings by dominoes of the plane on the other, also known as dimers or perfect matchings if you look at the graph. And people want to know how many there are asymptotically. So the basic theorem in the subject, of course, is the matrix tree theorem. And just for notation, let me just review. So the degree matrix is a diagonal matrix which gives the number of edges incident to a vertex. The matrix is indexed by the vertices, row and column. Adjacency matrix has a number of edges joining x to y as the entry indexed by x and y. And the graph Laplacian is the degree minus the adjacency matrix. Matrix tree theorem says for any vertex x, if you subtract the row, if you delete the row in the column indexed by x from the Laplacian, you go from a singular matrix to a non-singular matrix whose determinant is the number of spanning trees for all x. Let's just look at some examples. In the square lattice or in the torus, if you look at n by n portions, 1 through 7, this is how it grows. Of course, there are more in the torus because there are more edges. But you can see approximately how it grows if you turn your head. Looks like a parabola. So the exponential growth rate is quadratic. And why is that? So this is a natural kind of asymptotic we're going to look at. If you think about it this way, pick any single vertex and call that the root of the tree, and direct the tree with all edges in it going to that vertex. Then each vertex in the graph to the root, each vertex has exactly one, except for the root, has exactly one edge leading to the root. So if I think about this tree, it's a way of choosing directions to go, one direction from each vertex. And I want to know how many choices are there on average per vertex. So that's a natural way of looking at the asymptotic. So that, in other words, is saying the log of the number of spanning trees divided by the number of vertices. That's the number of choices per vertex, essentially. And take the limit when the number of vertices goes to infinity with some family of graphs, in some sense. So we need to make sense of what does it mean for the set of graphs to tend to infinity within some family, and how can we calculate what this limit is. Okay, so that's my topic. Any questions in the background or anything? So in the cases we've looked at just before, the square lattice and the torus, it's well known from the connection to dimers that the limit exists and that both limits are the same, namely 4g over pi, where g is Catalan's constant. Now, if you did this in d dimensions, the limit is also fairly well known. And again, if you look at boxes or tori, you get the same limit, and it's a integral over the d-dimensional unit cube of this function. So it just so happens that when d equals 2, you can give another evaluation of that. So that's one situation where the answer is well known. Another situation where it was done 20 years ago is that of random regular graphs. So this picture, there are 60 vertices, and each one is connected to 3 others in a random way, uniformly chosen, and connected. So if d instead of 3 is the degree in general, then McKay proved in 83 that if you look at the number of spanning trees divided by the number of vertices, the log of the number of spanning trees over the number of vertices tends, with probability tending to 1, to this number here. Okay? And he asked some questions about generalizing his result. So one thing which is true here for a random regular graph is that the girth tends to infinity. That is, the length of the smallest cycle tends to infinity with probability tending to 1. And he asked if that sufficed for this result among d regular graphs, or even more generally, if the number of vertices that lie on a cycle of a given length, the proportion of vertices that lie on a cycle of a given length tends to 0, whatever the length be. Okay, let me repeat that. For any r, I look at all cycles of length r in my d regular graph and look at how many vertices are on such cycles divided by the total number of vertices, that should tend to 0. That's weaker than the girth tending to infinity, which would say there are no such vertices eventually. But just the proportion tends to 0. He asked, is that enough to get the same limit? Okay. And as I'll show, the answer is yes. And that
graph doesn't have short line.
Yeah, why does the girth tend to infinity?
Right.
For
Random distributed.
well, so if you have to compute, given a cycle, what's the chance that that cycle occurs?
For example, triangle, the random measure is something like random graph with edge probability d over n. Then,
The Erdős-Rényi model?
yeah, and the count number of triangles could be.
That's not the same. The graphs really don't look the same.
I understand, but in terms of this computation, that's what I
didn't understand.
For example, number of triangles.
Yeah.
The expected number is constant.
Expected number is constant. I don't think that's true. At least I know it's true that the girth tends to infinity.
Anyway, that's slightly different from what I know. There is already short cycle. Because it's normal than other people always computed this conditional number of cycles. And we can discuss it later.
Okay. Anyway, this generalization that he asked about, he knew would be the most general case where you would get this limit if it's true. And I'll show that as well. So let me tell you one more reason why people are interested in calculating these asymptotics. Suppose we have an infinite connected graph G, and there's a way to define an analog of spanning trees or random spanning trees on G. That is the following. Let G sub n be the ball of radius n centered at some fixed vertex of G, doesn't matter which. Then Gn is a connected graph, and consider a uniformly chosen spanning tree on Gn. Let's call that measure mu sub n. So it's a measure on subsets of edges of G sub n. So P-Manual 91 showed that the weak limit of this measure, this sequence of measures mu n exists as a measure on edges on all of G. So in other words, given any finite set of edges, the probability of what you see in that finite set as n tends to infinity has a limit. That's what I mean by weak limit. And this weak limit we now call the free uniform spanning force measure, USF. Which turns out to be a very interesting measure, connected to many things. Now, one thing in particular that that's interesting in special cases is the following. Suppose G is a transitive graph, a vertex transitive graph, so that means for any two vertices there's an automorphism of the graph that takes one to the other. So it looks the same from any vertex as from any other. And suppose it also has polynomial growth, like z to the d. Then there's an entropy per site of this measure, which is the following. Look on G sub n and all possible subsets of the edges of Gn, omega. Each subset has a certain probability that that's what you see on Gn. So the square brackets omega sub n is the set of all subsets of, subsets of all of G, which on Gn agree with omega. It's like a cylinder set. So look at the probability that you see omega in Gn, that's USF of this, and take minus that times log of it. So that, summing that up, is the entropy of this measure restricted to this set. This by definition of entropy. This grows as n grows, as this G sub n grows. So you normalize it by dividing by the number of vertices in Gn. This limit exists, and that's a measure of the amount of randomness there is in the USF measure per site of the graph, because it's an infinite graph. Now, They proved, but incorrectly, in the same paper I corrected the proof, that this limit is equal to the asymptotic growth rate in the sense of the number of spanning trees of G sub n. So this is an interchange of limits that these two are equal, because if you looked at a uniform spanning tree on Gn, the entropy of that measure is just the log of the number of spanning trees. If all of these probabilities are the same and they add to 1, it's just the log of 1 over one of those probabilities, so the log of the number of spanning trees. So this is a kind of interchange of limits, so it's natural to expect that that's what you would have, because this is gotten as a limit of uniform measures. But it's not immediate, it's not automatic. Anyway, that's another reason why one does want to know what that limit is. So, we're going to be looking at these limits and taking them within families of graphs. And so what do I mean by going to infinity within some family? So there are two cases, and I'm going to present everything in the simplest case first and then later in the general case. Simplest case will be the following, and that's the case that we've seen so far particular examples for. So in the square lattice or the torus, we see in the torus, if I look at a neighborhood, all the neighborhoods are the same. Torus is a transitive graph. In the square, it's not, but almost all of them are the same. Near the boundary, they're different. And for a random regular graph, almost all the neighborhoods are the same. For a small neighborhood, it looks, because there are no cycles, small cycles, it looks like a tree. So the general definition in the simplest case is, for each r, if I look at the ball of radius r around a uniformly chosen center of G sub n, so I get a distribution on graphs, centered graphs, rooted graphs, that should converge in distribution to the ball of radius r in some fixed limiting vertex transitive graph G. So in the case of z to the d boxes or tori, the limiting graph is z to the d. In the case of the random regular graph, the limiting graph G is a regular tree. So let me state this more precisely, or especially for those not used to convergence and distribution. So a rooted graph, GO, is just a graph with some vertex picked out O called the root. A rooted isomorphism of rooted graphs is a bijection of the vertex sets which preserves adjacency and takes one root to the other. So let's let x sub r of Gn be the rooted ball of radius r around a random uniformly chosen root of G sub n. And b sub r, so that in G, we're looking at a vertex transitive graph G, and the limit is only one ball. It looks the same everywhere. So just call b sub r of G the rooted ball of radius r. If the probability that these are rooted isomorphic tends to 1 for every r, then we say the random weak limit of Gn is G. Okay? So here's the main theorem in this special case. If that happens, if the random weak limit of Gn is G, and we have a technical hypothesis, the average degree of Gn is bounded, it's fairly mild, then this limit exists, and I can evaluate it. I'm calling it the tree entropy, and I have some formulas here. Now, before going into what these formulas mean, let me say something about this theorem that's useful even without having a formula for the limit. Namely, that the fact is the limit only depends on the limiting graph, right? So if I changed G sub n in some small way, like in some set of vertices that have vanishing proportion, that would not change the limiting number. So for example, if I compare the box with the tori, I only change the boundary, and that's why the limits are the same. So before, it was just you calculate them and you see you get the same limit. But here's a general explanation of why they're the same. Of course, it also answers McKay's question, because McKay's question in this language was precisely, if I have a set of graphs whose random weak limit is a regular tree, then do I get this limit that he had? So the answer is yes. So what is this tree entropy? I'm going to give two formulas, as I said, one with a trace or a determinant, and one which is here, and a probabilistic one which I'll give later. So the matrix tree theorem said that tau was given in some way by a determinant, and this is somehow, you take a log of it and normalize it. So this capital D is a normalized determinant of the graph Laplacian on the infinite graph. So I have to tell you what that means. Now, well, I'm going to define it in terms of another concept which I have to define, a normalized trace. It's capital T here. So if you think about the determinant of a matrix as the product of the eigenvalues, the log of that is then the product of log of the eigenvalues. Sorry, the log of the product, which is the sum of log of the eigenvalues. And log of the eigenvalues are the same as the eigenvalues of a log of the matrix. So in other words, it would be the trace of the log. Okay, so, and there are situations, like the present one, but in general context, where one defines determinant in terms of a trace if one has a trace on a von Neumann algebra, and that's the situation here. So what is a trace in this setting? So I have this operator, which is really an operating on little L2 of the vertex set of G. And I'm omitting technical details. You're free to ask me if you want. And you take log of this operator, it's a positive definite operator, and then apply it to this vector, which is 1 at O is some fixed vertex of G, is 0 elsewhere. It's a vector in L2. Take the inner product of that with itself. In other words, if you look at the standard basis of little L2 of the vertex set, then this is any one of its diagonal elements, the matrix of this operator in that basis. So because G is transitive, the diagonal elements are all the same. So if you wanted to take trace in the ordinary sense, you'd be having infinity times that. But the normalized trace is just one of them. So right now I'm just giving you an intuition about why this should make sense as a definition. Later I'll give you more mathematical reasons. Now, I also want to show you how you use this to calculate things. Okay? So let's do the classical formula in z to the d. So we want to calculate the tree entropy of the nearest neighbor graph on z to the d. I need to use the fact that there is an isometric isomorphism between the space we're interested in, little L2 of z to the d, and big L2 of the d-dimensional unit cube, given by the Fourier transform. A goes to A hat. So if I have a sequence A in little L2, I define A hat on this space by A hat of S as the sum of A of K, e to 2 pi I, K dot F. So K is a d-dimensional vector of integers, and S is a d-dimensional vector of numbers between 0 and 1. Okay? So the important thing here, this is obviously a linear map, and it's an isometry. It preserves the inner product. So this is the inner product on sequence space. This is the inner product on the function space, and they're the same. Okay, that's a trivial theorem. That's just the fact that the complex exponentials are orthonormal. Okay? Now, I want to do this because I'm interested in operators on this space. And it's much easier with the operators I'm interested in to analyze them on this space. So the operators are of a special form, and to see that, let's look at some special operators. Suppose I have a function f which is bounded on the d-dimensional unit cube. Then there's an operator of multiplication by that function on big L2. So for any g, let's write m sub f of g to be f times g. What are the matrix entries of this operator, m sub f? So I'm using, and the unit vectors here correspond to the complex exponentials here as the basis vectors. So we'll just call them 1 sub k hat and 1 sub j hat. Suppose my function f was one of these a hats. They all are, but so let's look at this is the jk matrix entry of the multiplication operator. So what is it? Well, by definition, it's this inner product. So you multiply this function by a hat of s, then you multiply by the complex conjugate of this function and integrate. So I can combine these two complex exponentials into one, j minus k. And so I see that this is just the inner product between a and 1 sub j minus k, by the isometry. In other words, it's the j minus k entry of a. So these are tuplets matrices. They're constant on diagonals parallel to the main diagonal. Now, the Laplacian is the matrix I'm interested in. I want to take its log. So I claim the Laplacian is an operator like this. It does have the form a of j minus k for the jk entry, where a is this little sequence here. It's 2d if n equals 0. So that says the degree of every vertex is 2d. Okay, 2d nearest neighbors. It's minus 1 if the norm is 1. And it's 0 otherwise. It's only connected to nearest neighbors. Okay? So this operator corresponds to multiplication by a hat. A hat is some trigonometric polynomial. So the log of this operator corresponds to multiplication by the log of a hat. So why is this? I'm claiming that log of a multiplication operator is multiplication by the log of the function. Well, just think of multiplication by the square of a function. That's the same as the square of multiplication by the function, right? Polynomial of multiplication by a function is multiplication by the polynomial. Same is true for logarithm. Okay? So what am I interested in? I'm interested in the diagonal entry of this operator. Right? That's the definition. The tree entropy is the integral of log of a hat. Because I just take this, I multiply this by the constant function 1, which corresponds to the identity, 0, and take the inner product of that with 1, which means multiplied by 1 again. That just gives you the integral of a of log hat, the integral of log of a hat, and a hat is this, which if I just combine all, opposite complex exponentials, gives me these cosines, and that's that classical formula. Okay? That's how one can calculate with that formula. Now, this, though, actually does not make it, this particular formula does not make it so easy to calculate McKay's formula. And in fact, to do that calculation, we need the other formula for tree entropy, which is the probabilistic formula, and this is really the key to the proof, and I'll show you later. So here's a completely different formula. G, again, is this vertex transitive graph, and the tree entropy also is equal to the log of the degree of any of its vertices minus the following series. 1 over k, p sub k, where p sub k is the return probability if you start a random walk and take k steps, all choices being equally likely at any point among neighbors, that you're back at the starting point. As we'll see later, this is really key because this, well, and especially an analogous formula for finite graphs, this is a series in terms of local quantities. And since we're taking a limit, and the limit is a weak limit, it's only basically defined as preserving local quantities, we'll need such an expression to take limits of. But let's use this formula now to see how this one can be used to calculate and to compare. So how do we calculate this? Well, there's a return probability generating function for these, just put them as the coefficients of a power series. Then this sum is gotten by subtracting 1 because p sub 0 is 1, dividing by z, and then integrating from 0 to 1. And this is useful because this function is known in other cases that we don't have the Laplacian, log of Laplacian for conveniently. For example, when we have a regular degree of degree d, here's a formula for this generating function. Due to Keston when d is even, and not clear who in general, but it's not such a hard formula. So you can just integrate this. This has an elementary integral, and that gives you McKay's formula and the generalization. Okay? Now, this is useful not just for calculation, but also for comparison. Suppose I had two different limits. I might not just have a regular tree as a limit, but I'm considering regular graphs of degree d, and maybe they don't have a random weak limit, which is the tree, but some other thing. They do have cycles. Then I claim that the tree entropy is less. The asymptotic growth rate for these other graphs is strictly less than that for the ones which have a tree as a limit. This is a theorem of McKay, and here's a simple proof. Just use this formula. So if I have graphs of degree d, then this first term is the same, but these other terms are not. And in fact, the d-regular tree covers any d-regular graph. There's a graph homomorphism from a tree onto any d-regular graph. That is surjective. And so return probabilities on G1 are less than or equal to what they are on G2 if G1 covers G2. Because you take a path and you project down, you may return down here, but you don't necessarily return up there. But if you turn up here, then you return down there. And so, and this inequality is strict for some k if these graphs are different. And so I get this strict inequality. Okay, so that's the what happens in a special case, although I haven't given any proofs. Let me tell you the general case. So this would be the case, as we'll see, with Erdős-Rényi graphs. They don't have a deterministic limit, they have a random limit. And this is sort of the most general case that you can consider. So instead of having a fixed graph G as a limit, what we'll have will be a probability measure on rooted infinite graphs as a limit. So called rho. So when is that going to be the random weak limit of a sequence of finite graphs, Gn? Well, again, I look at the random ball, a ball of radius r centered at a random root of Gn. That is some random rooted graph, and that should converge in distribution to the rho distribution of the ball of radius r around its root. So I get some random graph with a root, look at the ball of radius r, that gives me some random graph, and these ones should converge to that in distribution. Which, again, to spell that out precisely means if I have, as before, xr of Gn is the ball of radius r around a uniform root of Gn, now I have this random limiting graph, radius r, then the probability that this is isomorphic, rooted isomorphic to any given h, should tend to the probability that that's what I see in the limit for any r, any h. Okay, that's the convergence in distribution. It's looking more and more like rho. Now there's a special case which we will be interested in. If Gn is itself random, then rather than this being a number, it's a random variable depending on Gn, and I want that this random variable should converge in distribution or measure to this number. Okay. Now, before I give you an example, I just want to tell you what the main theorem is in the general case because it's so similar, and then we can analyze our example right away. So if the random weak limit of Gn is rho, and the average degree of Gn is bounded, then this has a limit, what I call the tree entropy of rho, and it's almost the same. It's a normalized determinant, I put in a subscript rho, which is defined via normalized trace with the subscript rho, and what it is the following. It's the same as before, except that G and O are now chosen according to the probability measure rho. And likewise, the other formula also is valid when G and O are chosen with probability measure rho. So let's see an example. So here we have 100 vertices, and each pair is connected with probability 0.02 independently. That in general is not a connected graph. However, as probably everyone here knows, there's a giant component, one whose component is of order 100, and that's shown here. So we'd like to know about how many spanning trees that has. So this is the usual Erdős-Renyi model of random graphs, where you have n vertices, and each pair is connected to probability p independently. We'll be choosing p equals c over n. C is fixed constant bigger than 1. Now, the entire graph, I want to look at the giant component, but first, it's simpler if I look at the entire graph, random graph, has a random weak limit, which is sometimes denoted PGW of C. That's a tree. Poisson, Galton, Watson of C, where, oh, I know the source of your confusion, maybe. So here, for example, although there are triangles, they're very sparse. Okay? If you look at a neighborhood of any point, you won't see any.
But in the random regular graph, it's true. In the neighborhood of any point, you don't have triangles, but somewhere you have.
Right.
The graph is not tending to infinity.
Oh, I'm sorry. Right. Okay. Yeah. Okay, so this means you take a Galton-Watson tree, so you start with one vertex that has a Poisson distribution with parameter C of number of children, and then each of those independently have the same number of children, that is from the same distribution, and so on. And that's denoted PGW of C. That's for the whole graph. For the giant component, the random weak limit is sometimes denoted the same with a star, which is the same random tree conditioned on being infinite or non-extinction. So that's our row. The giant components have a random weak limit, which is PGW star of C. And that's not a fixed graph at all. So we're interested in its tree entropy. Nevertheless, the tree entropy is a number. It's not a random variable. So the giant components all have the same, with probability 10 to 1, all have the same asymptotic growth rate for the number of spanning trees. This tree entropy here. Now what is it? Unfortunately, I don't have a formula. And I unfortunately don't know that much about it. I do know it's positive, and I do know that as C tends down to 1, it tends to 0. Presumably, it's continuous and strictly increasing. But unfortunately, I don't know how to prove that. I haven't tried real hard to prove continuity. Work more on the increasing. Why is it not obvious that it's increasing from the definition? So in the definition, if C increases, the giant component gets bigger, I get more edges, there are more spanning trees. But I've also divided by the number of vertices, which has gotten bigger. Nevertheless, it should be the case that the numerator outweighs, the increase in the numerator outweighs the increase in the denominator. No, I don't know that.
So there was a sum involving the return probabilities, the
Right,
series.
right.
Do you believe it's monotone term by term that you can't prove it?
That's, no, the degree also increases. There was the first term not in the series, which is log of the degree, which also increases. However, it's probably true that the other terms, that what you said is also true, that just for the series. But yeah, you can't prove that. So, it's time to say something about proofs. First, I've given you two entirely different looking formulas for the tree entropy. And why are they the same? As I said, the proof goes really by showing the probability formula and using that to show the trace formula.
Wait, can I interrupt?
Yes, sure.
You had an assumption that the degree is bounded.
Average degree.
Oh, the average degree. So it doesn't have
Right. Okay, so I have this, what I call the trace of this logarithm of the graph Laplacian. Now, the graph Laplacian, I can factor this way. This is the degree, the diagonal degree matrix, D sub G, and P sub G is a transition matrix for simple random walk, and the I is just the identity. So if I divide each row by the degree, I get I minus PG. Now, this is the log of a product, and I claim that I can replace that by the sum of the logs, but that's because it's inside a trace. Of course, I have to justify that this is a trace, like a normal trace you're familiar with. But this is true. Okay, so assume that for now. Now, this log I can just expand as a power series around 1. Right? So I get the trace of this operator. And now just use the definition of the trace. It's the diagonal element, right? So just I choose GO according to rho. This is just a diagonal matrix, so the log of this matrix is easy to calculate. It's just put the log on the diagonal. Okay, log of the degree. Here, the diagonal entry is just the return probability. Okay, so that gives the formula. That's why they're the same. But, of course, the crucial thing was that this was a trace. So why is this a trace? And the crucial property of the trace that I'm using is that that multiplication is commutative inside. Okay? So this is joint work with all this in another paper, which isn't finished. So let me do the simplest case first for why this is a trace. Namely, that rho is carried by a single graph, and not only a transitive graph, but in fact a Cayley graph of a group, finally generated group gamma. Okay? Let's do that case first.
Can you remind me what the definition of this capital trace is?
Yeah, it's this. Trace of an operator is you apply the operator to, this is the diagonal element of the operator for random GO. So in other words, you apply the operator to the vector which is 1 at O and 0 elsewhere. It gives you a vector. Take the inner product of that with that same vector 1 sub O. So, right, these operators are, you should think of them as a family of operators for each graph, right? So in the simplest case, I just have one graph and a single operator. Okay, and it's just a diagonal element of that. Now, when I say the diagonal element, I'm only interested in certain operators, like the ones that arise here. They're gamma equivariant operators. That's why they are the same on the diagonal and elsewhere. So gamma equivariant means that if I look at the yx entry, it's the same as the gamma y, gamma x entry for any gamma in the group and any xy in the group. So if I start with an operator like this, like the Laplacian, which is of this form, then I take a logarithm, for example, it will still be of this form. That is, still be equivariant. Okay? Any questions on what I'm about to prove? Yes, Henry.
So where are you using this commutativity of the trace?
Where
is it being used?
It got used right here to say that log of a product is the sum of the logs. That's not true for matrix multiplication. Right. But it's true inside a trace. If things are commutative, then it's no problem. Right?
There's some more general formula that the log of a product in one way plus or minus the other is something of the expression of the commutators.
Right. With all sorts of commutators, it's long and complicated. What?
It quickly gets out of hand.
Yes. Right. Any other questions before I move on? Okay. So the proof that this is a trace is going to use the mass transport principle. So let me remind you or tell you what that is. So in this case, gamma is a countable group, and if I have a function on gamma cross gamma to the non-negative reals, including infinity, which is diagonally invariant, so f of xy equals f of gamma x gamma y, then if I look at the sum and where I sum over one variable, it's the same as summing over the other variable. So let me prove this if you haven't seen it. F of OX by diagonal invariance is the same as f of x inverse O, x inverse x, which is f of x inverse O, x inverse comma O. And I'm summing over all x. So that's the sum of this over all x, but the sum of over all inverses is the same as over all group elements. That's it. Oh, by the way, so this is not negative, so I didn't have to worry about issues of summability. And I'm going to apply it, though, to functions which are not non-negative. However, if you have summability, if you know summability in advance, then it's still true. Take the positive and negative points. So here's the proof that I have a trace. So the trace of ST is the diagonal element of ST. Now, put this S on the other side by taking its adjoint. The other side of the inner product. Now, I have the inner product of two vectors. Expand each of these vectors in terms of the standard basis. And so it's just, and so it's just the it's just the product of it's the sum of the product of the coefficients. There's a complex conjugate here, but it's written the other way, so that's correct. Okay? So that's just the inner product in these two vectors. Now, take this S and put it back on this side. Now I have a function, here's a function of O and X, summed over all X. Apply mass transport, switch O and X. I get this. And now you can say that's the same as switching S and T. So it's the same as the trace of TS. Okay? Now, there's an analogous principle that works in the general case. Let me motivate that by why this is called mass transfer principle. There's a conservation of mass on finite graphs, which is obvious. If G is a finite graph, and that'll be useful to state, and U is a uniformly chosen vertex of G, and I have any vertex, that's not correct. This codomain should be the reals. Sorry. Oh, and this should be on V of G cross V of G. Sorry. Function on V cross V to the reals. Okay? Then if I look at, and I think of this as how much mass goes from the first vertex to the second vertex. And so this is how much mass goes out of a uniformly chosen vertex on the left. And on the right is how much mass goes into a uniformly chosen vertex. Okay? So this is obviously the same, because if I didn't take expectation but just summed, it would be the total amount of mass going around. And there's nowhere for the mass to go. Nowhere to leave, okay? So, as Itai Benjamini and Oded Schramm noted in a paper on random weak limits of planar graphs, random planar graphs, planar triangulations, that if you have a random weak limit of finite graphs, then an analogous principle holds, which extends the one I mentioned, mass transfer principle before. So, of course, we are interested in such random weak limits rho. So you get the following mass transfer principle by taking a limit of this. So it's useful to write this as expectation of a uniform vertex because that's what tends to rho with the root. So f, of course, now it's on a random graph, so it has to be phrased slightly differently and carefully. You have a non-negative Borel function on the space of graphs with an ordered pair of distinguished vertices. So first vertex, second vertex. So f of a graph, first vertex, second vertex, okay? Assuming that f is invariant under automorphisms of the graph. So that means given g and xy and gamma and automorphism of g, f, the amount of mass sent from gamma x, gamma y is the same as from sent from x to y. Okay? Then, if you take the amount of mass going out of the random root, it's the same as the amount of mass coming into the random root. Okay, that just follows by taking the limit here. Expectation is just now written as an integral instead. So, as we saw, this was the key to why we have a trace. Well, maybe I should skip this because we're running low on time. Well, I don't know. It's up to you. We started early, right? We're done early.
I think
This is similar to this.
similar
Yeah.
to what we had before.
Right. Yeah. So anyway, you just have to make the right definitions and use that more general mass transfer principle, and you get the same result. You just put expectations where you around the proof from before. Okay. So this proves what I've done now is tell you why the trace formula and the random walk formula are the same. I haven't proved either one. So it's now time to prove the probability formula, which I said is the key because it expresses it as a sum of local quantities. So what we use is an alternative version of the matrix tree theorem that's due to Runge and Sachs in 1974. It says the following: number of spanning trees of G is, well, there's this determinant prime. So we're interested in I minus a transition matrix with simple random walk like before. This is a singular matrix, so we don't take as a determinant. We take the product of all the non-zero eigenvalues. And then you have to normalize by multiplying by all the degrees and dividing by the sum of all the degrees. I can show you the proof here if you like. Go run through this for you. Okay? So, we calculate the coefficient of t in this determinant of the Laplacian minus t times the degree matrix in two different ways. So one way, we're going to use cofactors of the diagonal in the matrix tree theorem. So if I look at this, what's the coefficient of t? Well, when will I get t? This is just multiplying a diagonal matrix, right? So I can only have one t, one diagonal, one t, and then the cofactor of that entry. Well, the cofactor we know, okay, so here's the cofactor. And t is multiplying this minus multiplying by negative the degree. And there's all possibilities, okay? And the matrix tree theorem says that cofactor is just tau. Okay, so that's one formula for the coefficient of t. On the other hand, we can use the characteristic function of I minus p. So how is that? So this determinant, if I factor out this degree matrix, okay, which is just a diagonal matrix, then we know that delta becomes I minus pg and tg dg becomes I. So this, you see, is just 1 minus t times I minus PG, so it's a characteristic function. So this is preserved, and I just get the product over all eigenvalues of eigenvalues lambda of I minus P minus T. Okay, and what's the coefficient of T in here? Well, one of these is 0. One of these eigenvalues is 0. So I have to take minus T there, and everything else are the non-zero eigenvalues. And there's a minus sign there. And so comparing these two, the determinant of dg is this numerator here, and you get the formula. Okay, so here's the outline of the proof. So I said that we need this similar expression for a finite graph G in terms of a series of local quantities for the number of spanning trees. So here it is, minus log twice the number of edges, plus the sum of all vertices, log of the degree, minus sum 1 over k, return probability, starting at x, summed over all starting points x, minus 1. Now suppose this is true. Okay, suppose this claim is true. This is going to follow from Runge-Sachs. What do I want to do? I want G to be G sub n. I want to divide by the number of vertices of Gn and take a limit. This, this is basically log of something over the thing that tends to 0. This part gives me the average log degree, which is what I want. One of the terms I want. What about over here? Well, if I put 1 over the number of vertices inside here, well, this subtracting 1 is going to disappear in the limit if I take a limit term by term. And this tends to the return probability from an average, from a root, average center. So that tends to this. Okay? So if I can take term by term limits, then I get my theorem. And that's because these are local quantities and because it's a random weak limit, which is just a limit with local quantities. Okay? So all I need to do to justify it is interchange the limits. So, and prove that claim. So here's the proof of the claim. And this will also show you something about traces. This is an analogous formula. Very simple, though. So this is Runge-Sachs. The sum of the degrees is just twice the number of edges. Here's Runge-Sachs. Take the log. And so I get this here, I get this here, and this here. Okay? So far, it's just this last term which I want to change into this. Well, so let's call lambda the multiset of eigenvalues of P, except for 1. 1 is an eigenvalue of P. Simple eigenvalue if P is connected, if G is connected, so with multiplicity. So lambda is a negative 1 to 1, including 1. So log of this is just a sum of log of 1 minus the eigenvalues of P. Expand this logarithm in a power series. Interchange the order of summation. And now I see what this is just the trace of P to the K, except that I don't have the eigenvalue 1. And the trace of P to the K is just the sum of the return probabilities over all starting points for K steps of a random walk. So that proves the formula of the claim. So really the hardest part is some sort of bound that allows you to interchange the limit, which needs to be fairly general if you want to get this general theorem. Now, the following may well hold, seems likely, but I couldn't prove it, and this would suffice. So first of all, one thing we need to do is, in fact, you can't work with just simple random walk in general. It may be periodic, and those terms are not going to be universally bounded. Some of those return probabilities will be 0. You just have 1 over k. No good. Not summable. But it turns out you can show that you can use other random walks, like lazy simple random walk instead, where you stay where you are with probably 1/2, and otherwise you choose a random neighbor. and then you break the periodicity. And if we call Q sub G the corresponding transition matrix, so this is the kind of term that we want something so that we can apply the Weierstrass M test, so the base-dominant convergence theorem for series. So we need something so that if we multiply by 1 over k, we get something summable. Some bound that works for all graphs. So for example, this would work, constant over log squared k. And this may well hold, at least for any simple, it won't hold in general, but for simple graphs, simple connected graphs, this might hold. But unfortunately, I don't know. Simple means no loops, no multiple edges.
So that's some kind of fast mixing thing.
Right. It's a very weak statement on how fast it mixes. Very, very weak statement. So, I don't know that, but instead there's something else, and I won't go through the details, but there is a general result which says the following: have a transition matrix of a finite Markov chain which is reversible, as we have. Well, you define some minimum, if you think about electric conductance or weight of an edge, the minimum of pi of x, q of x, y for neighbors x, y. Call that C. And A is the minimum return stay probability, like 1/2. So this would be something in terms of the degree for a simple random walk. So here's a universal bound of the convergence to stationarity.
That's one of the number of edges, isn't it?
Yes, this would be 1 over the degree, or 1 over twice the degree if you stay with probably half. Divided. Sorry.
One over the number of edges. 1 over twice.
So it's 1 over the degree. Yeah, 1 over twice the degree divided by the number of edges. So if the number of edges over the number of 1 over the number of edges. Sorry, the degree over the number of edges. No, just 1 over the number of edges. Sorry. 1 over the number of edges. Or 1 over twice the number of edges. It's 1 over twice the number of edges. Sorry. Yes, I forgot to normalize. Yes. 1 over twice the number of edges. Exactly. So that 1 over it is the number of edges on top, which is, and this we're going to get to divide by the number of vertices, and that's where a bound on the average degree is being used. So my theorem could be generalized if I had something like this, for example, to G and P, without P being C over N, so not having average bounded degree. Although you can generalize it in that case for other reasons, they're expanders. So anyway, here 1 over root k is enough. And these, like I said, A is just going to be 1/2, and C, 1 over C is basically the number of edges. And when you divide by the number of vertices, that gives you a boundary. And when you add this up over all x, multiply by pi of x and add up over all x, that will give you what you want. So this is basically a standard theorem. Can be proved in a couple ways. But it's not really new. That's it. What's that?
Tim Thiel has this bound which talks about the... No, that's... Sorry.
Yeah, so of course, there are much better bounds if you talk about the... if you assume something on the conductance of the graph G and the isoperimetric constants. But if you don't want to use anything, then it's something like this.